Okay, this is part 2 of the section probably 7.3, we'll see about that, video on polar coordinates. Part 1 we talked about if you're given a distance and a direction, how to find an xy coordinate from that. In this video we're going to talk about doing that backwards. If you're given an x and a y coordinate, how can you express those coordinates in terms of a distance and a direction? Before I go into the process of doing that, I kind of want to talk about the difference between these two systems and why some of them might be used. These two systems, x and y coordinates, sometimes called rectangular coordinates, sometimes called Cartesian coordinates. This is sort of the coordinate system we're used to in mathematics, and this is very useful for just uniquely identifying points on a plane. In terms of real-world applications, it's pretty easy to think about x and y coordinates as like positions on a city grid. Like I personally have never been to New York City, but I've heard that the streets and the avenues are lined up in a very neat and orderly grid fashion. So if you're on the corner of 39th and 14th and you want to get to the corner of 53rd and 27th, you should just be able to look at your position as if it were a pair of xy coordinates and say to yourself, well, I need to go a certain number of blocks left and a certain number of blocks up, or a certain number of blocks right and a number of blocks up. I don't actually know how blocks work in New York City. Again, I've never been. But thinking this in terms of distance to the right and distance up, or if you have negative numbers, that would make it left and down. Thinking of these as perpendicular distances is what the theory of the xy coordinate system is based off of. So what we're doing as we switch into polar coordinates is we're kind of shift that paradigm. And now we're going to think of things in terms of, instead of a distance to the right and a distance up, we're going to think of things now as choosing a direction and going a certain distance in that direction. So if xy coordinates are good for navigating New York City, polar coordinates would be good for navigating the middle of nowhere, Kansas. If you're trying to wander around a cornfield in Kansas, you don't need to go only left and only right because there's a city in your way. You can just go directly to where you want to go on a diagonal, wherever that direction needs to go. This works also really well for airplanes. If you're trying to navigate in an airplane, or like on the open sea, if you're on a boat, you don't need to worry about only moving left and only moving up. You can choose your bearing. I think that's usually what your direction is called if you're navigating. You choose your bearing, you go a certain distance in that direction, that'll get you where you want to go. So that's kind of the idea here, is instead of, we're sort of switching from thinking about things in terms of x and y coordinates to thinking about things in terms of a theta, that's your direction, that's how you aim, and a distance, that's how far you go. And we call the distance r. The direction is theta, the distance is r. Polar coordinates we write as r theta. So it's still an ordered pair. This ordered pair still defines a position on a coordinate axis. It just defines that position a little differently than x and y axes would. So let's talk a little bit about, if you're given x and y coordinates, how you can turn that into polar coordinates. We'll start with something pretty simple. If x equals 4 and y equals 4. In rectangular coordinates, that means I go 4 to the right and 4 up, and I end up here at this point, 4, 4. If I want to transform this point into something that is expressed in polar coordinates, I need to know two things. I need to know this distance, and I need to know this angle. So I need my r, and I need my theta. We'll start with the r, because r I think is the easier of the two. Hopefully we have spent enough time doing trigonometry on the coordinate axes at this point to realize any point you choose on the coordinate axes will always, forever, and eternally make some kind of right triangle with the x-axis. Whatever point that is, you can draw in the straight line that connects the origin to that point. That'll be your hypotenuse. Drop a line, a vertical line straight down from that point to the x-axis. Bam, instant right triangle. And the nice thing about this triangle is, I know this distance, I know this distance, I have a right triangle that I know two of the sides of, so finding r, the hypotenuse, should be fairly straightforward. R squared equals 4 squared plus 4 squared. It's just a Pythagorean theorem problem. We've done plenty of those. We know how to do the Pythagorean theorem. So r squared is going to be 16 plus 16. That's 32. If r squared is 32, it means that r must be the square root of 32, which I can simplify that a little bit. I'm going to call that 4 square roots of 2. You may have also intuited this by the fact that this is an isosceles right triangle. But this will be 4 root 2 from the Pythagorean theorem. Not all of them will be nice right triangles, so it's good to know the full process. So that's r. I have a distance. It's a good start. Next, I need to know theta. So here's kind of the weird thing about theta. What we have here, I'm going to sort of expand this over here just a little bit. What we have here is a right triangle. At this point, because I've already found r, I know all three sides. I know that this is 4, that was given. I know that this is 4, that was given. I know that this is 4 root 2. And I'm drawing the 4 root 2 in a different color, and here's why. This information was given. This was given. This was derived. 4 root 2 is not given to us as part of the problem. It is something that we came up with partway through the problem. And that's going to be important because to find theta, we need to use some flavor of arc trig. The basic three options are we could use an arc cosine using the adjacent side and the hypotenuse. We could use an arc sine using the opposite side and the hypotenuse. Or we could use an arc tangent using the opposite side and the adjacent side. Those are the three basic options we have. I'm going to choose arc tangent all the time, every time. Because if we're given x and y coordinates, arc tan is always going to use the two pieces of information you were given. If you try to use arc sine or arc cosine, you have to end up using this derived information. And that's not always a bad thing. It's just, what happens if you did this wrong? Or what happens if you're taking a test or you're taking a quiz and you panic for a second and you completely forget how to do the Pythagorean theorem and you just don't have an answer here? It doesn't matter if this is wrong or missing or nonsense. If you use the arc tangent, you're always just using the given information and you don't have to worry about whether or not this was correct. It's free. So, for this particular problem, I'm going to say that the tangent of theta equals 4 over 4, the opposite over the adjacent. So the tangent of theta equals 1. And those of you following along with unit circles can probably tell me that theta equals pi over 4. This is kind of turning into a mess. Sorry about that. Let me reconvene this over here. I don't need the zoomed in version of this triangle anymore. I've discovered, using the Pythagorean theorem, that the radius of this circle, the circle that includes this point, should be 4 root 2, which is it's about 6, just a tiny bit less than 6. And using tangents, I've discovered that theta equals pi over 4, 45 degrees, right in the middle, which we sort of expected. When your x and y are both equal to 4, that means you have an isosceles right triangle, which has 45-degree angles in it. Maybe you just figured that out on your own without using arctan, which is great. Good. But the general process of doing this is always going to involve finding a radius using the Pythagorean theorem, finding theta using an arctan. Let me do one more like this, and then I will switch to the hard version. Okay. Let's look at what happens if I want x to equal let's say I want x to equal 7 square roots of 3 and y to just equal 7. This will be a good one. So 7 square roots of 3 is probably 15 or 16-ish, and y is just 7. So we're looking at a point that's out here-ish. Bigger x value than a y value. It's right there, approximately. I want r and theta for this point. To get them, I'm going to draw the diagonal. This distance needs to be r, and I need to find that. And I need to draw this angle, and I need to get this angle. Again, I'm going to start with distance by dropping a vertical line here, making a right triangle, getting the hypotenuse. R equals, or r squared I should say, equals 7 root 3 squared plus 7 squared. So 7 root 3 squared should be 49 times 3, which is probably 3 less than 150, 147. 147 there. 7 squared is 49. So r squared is 196, which means that r should be 14. So far so good. I need to find theta, and I'm going to use the tangent here. The tangent of theta should be the opposite side. That's y, which is 7, divided by the adjacent side, that's x, which is 7 root 3, which means this is 1 over root 3 after you cancel the 7s, which is the same as root 3 over 3 if you're simplifying it. The angle that has this tangent value looks like it should be pi over 6. So we'll call it pi over 6. It's not so bad. Pretty straightforward. Pythagorean theorem to find an r. Arctangent to find a theta. time to start doing the tricky stuff. Let's say x is negative 2, y is negative 2 root 3. Or no, I want to do positive. Positive 2 root 3. Let's look at where this point probably is. 2 back on the x-axis, 3 and change up on the y-axis. We're looking at a point that's right here. So, I'm going to draw my diagonal. This is the hypotenuse, the radius. I'm going to draw an angle. This is theta. Doesn't fit quite inside the triangle, but we all know that angles always start from positive x. And let's do this. Radius, I don't need all of this down here. Radius squared equals negative 2 squared plus 2 root 3 squared. So this will be 4. This is going to be 4 times 3 plus, so that'll be 12. So radius is 4 plus 12 is 16. Sorry, radius squared is 16. So the radius is 4. So far so good. It's not so bad. I need theta. The tangent of theta is going to be the opposite of this y value. 2 root 3 over the adjacent, this x value, negative 2. So that's going to be a negative root 3. So theta should be the arctan of negative root 3, which, plug that into your calculator. I'm pretty confident that you will get negative pi over 3 as your angle. We got a radius, we got an angle. We type them both into MyMathLab and we hit enter. And MyMathLab says that's incorrect. And then we cry about it. Maybe we flip the table. I don't know. Depends on how heavy the table is. Hopefully we don't get too frustrated. But there's some frustration to be had here. We followed the steps. Nothing here is incorrect. I put in my x value, my y value, I squared them both. I got 16. I got square root of 16 is 4. That checks out. These are in the right order. Y goes on top, x goes on the bottom. This is opposite over adjacent. That's the tangent value. The arctan of this is negative pi over 3. What's the problem? Why is this incorrect? Here's why it's incorrect. Negative pi over 3 is down here. If theta is negative pi over 3 and r is 4, this is a quadrant 4 point, which is not what I wanted. The first thing I did when I got this problem was I drew it, and what I drew was a quadrant 2 point. If I start with a quadrant 2 point and try to tell MyMathLab that it's in quadrant 4, of course MyMathLab is going to tell me that I'm wrong. This is not correct. But this is the steps. How do you adjust the steps to account for something ending up in the wrong quadrant? For this problem, the issue lies in the arctan. We've talked a lot before about how arctan is range restricted. Arctan will only ever give you angles that are in quadrants 1 or 4. If you've got a quadrant 1 point, great. Use the arctan, no problems. If you've got a quadrant 4 point, cool, use the arctan, no problems. If you have a point in quadrants 2 or 3, the arctan will never give you the correct angle, because the arctan will always give you a quadrant 1 or 4 point. So there's two options. There's two things we can do to adjust this. One is we can adjust the angle. This angle is pointing in the exact opposite direction of what we want it to be pointing. It's going down negative pi over 3, we want something going up this much. So one thing we can do, I'll put option 1 in green. If you get an arctan angle that's in the wrong quadrant, you can add pi to it. If your point is in quadrant 2, it means that your tangent value will be negative. Arctan will give you a quadrant 4 angle. Adding pi to your quadrant 4 angle will put it in quadrant 2, and this will solve your problem. The other thing we can do to solve this problem is r squared equals 16, is another thing we've talked a lot about. R squared equals 16 has